Section 9.3, we're going to encounter two more tests to help us to know when series converge or diverge. So far, we've seen, or at least our biggest focus has been on focusing on convergence, and we've talked about the fact, at least somewhat cursory, that we can't always figure out what a sequence converge or a series converges to. So generally, speaking, we need to be able to test for convergence without finding the limit of the sum. We'll say without finding the limit itself. And in fact, sometimes it's not even possible to find the limit. So we've encountered the geometric series, which was lovely, and we can find the limit. We encountered, what was the other one we encountered last time where we were able to find the sequence or the series value? Which one was it? The telescoping or the collapsing sum. That was one where we were actually able to find the series value. But sometimes this isn't possible. So here, that is in this lesson, we will take a look at additional methods and these won't give us limiting values. Okay, so they leave a little bit to be desired. They still will tell us where something converges or diverges. And sometimes it's the best we can do. All right, for starters, we're going to take a look at Theorem 9.10, which says the following. If f is a positive, continuous, or is positive, continuous and decreasing, so those are our conditions, for x greater than or equal to 1, and a sub n equals the function value at n, then the summation from n equal 1 to infinity of a sub n and the integral from 1 to infinity of f of x dx either both converge or both diverge. So what we're doing is we're trading out a summation for an integration. And in integration, you have lots of techniques that we don't yet have things that are equivalent to inside of summations. Notice what this doesn't say. It says that they either both converge or they both diverge. It does not say these are equal to one another, right? So just because I'm able to find the integration component and find it exactly, which I sometimes am, doesn't necessarily mean that that's an equal statement to what the summation is. It just tells us whether it converges or diverges. So we're going to do an example I'll need more space. We'll just flip to the next screen. And the example we're going to do has the following directions. So we're going to confirm that the integral test, that's what that one, I didn't write it on the previous screen, but that's the integral test. The integral test can be applied then use it to find whether it converges or diverges. So to find convergence or divergence. And this is the summation we're looking at on this one. It's the summation from k equal 2 to infinity of 2 over k natural log k. Okay, so what does it mean, the first part of the directions? It says, confirm that integral test can be applied. Well, at the very beginning of the integral test over here, there were some conditions that we said had to be true. Things had to be, the function has to be positive. The terms, anyway, have to be positive. They have to be continuous. The function itself has to be continuous. And then it has to have decreasing values. So if the integral test can be applied, this piece right here is going to be the a sub n that's going to match up to the f sub n that it's talking about, which means that we're looking at the function, of 2 over x natural log of x. That's what we're looking at in terms of the fn. And we're talking about whether fn itself is continuous, whether it's positive, and whether it's decreasing. So let's just run through each of those and make sure that they work. So the first one was that it's positive. Now, this tells us that the k value starts at 2. And similarly, you could talk about x value starting at 2. When x is 2 and beyond, is this always positive? Yeah, it's always positive. So x itself is positive. It's in the denominator. The natural log of x when x is bigger than 1 is also positive. So this one is positive because all the pieces are positive, right? Positives multiplied, divided, we get positives everywhere. The second thing is to determine if it's continuous. Well, continuous functions, I guess we haven't checked it yet. I marked it like we had. Continuous functions have continuous pieces, right? So this is a rational function. Rational functions are going to be continuous unless there's a 0 in the denominator. If there's a 0 in the denominator, we're going to have a problem, or if some piece of the denominator itself has continuity issues. Well, x in the denominator is continuous, right? Line y equal x is continuous. The curve y equals natural log of x is continuous as long as you're bigger than 0, right? The natural log of x graph looks like this, roughly speaking, with the x or the y-axis being an asymptote. So it's continuous. When you multiply two continuous pieces together, you get something continuous. So the only possibility that would be a problem is if the denominator equal to 0. But the denominator is only going to be 0 if x itself is 0, right? Or actually if x was equal to 1. The natural log of 1 would be 0. But neither of those things can happen because I'm starting with k equal to 2. Right? The k is equivalent to the x in this function notation. So this is continuous. And the reason is really because the x value is greater than 2. So x and ln of x are continuous, and they're not equal to 0. Right? Not equal to 0 would create a continuity break as well if that were the case. So yeah, it's continuous. The last piece is to confirm that it's decreasing. These are the three things. So why would this function be decreasing? Well, let's think about the denominator. As the denominator has values of x that are increasing, what's going to happen to the whole denominator as a whole? Denominator.
It's going to approach 0.
Okay, so the denominator is going to get increasingly large. The fraction, I think, is what you mean is going to approach 0, right? Yeah, so this denominator, x is going to infinity, right? The natural log of x is going to infinity. We have two pieces that are getting infinitely large, and they're getting, they're increasing themselves. So when I divide by something that's increasing, I'm going to create something that's decreasing. It's going to approach 0. So this one is decreasing, and the reason it's decreasing is because the denominator is increasing. Right, that's really the why. Okay, so we've done the first part, confirmed that the integral test can be applied. It can be applied. So what that means is that instead of concerning ourselves with the summation, we can now look at the integration, the integral of 2 over x natural log of x. And this will go from 2 to infinity. We swap out the limits of integration so that they match the k values over here in the summation. So it's 2 to infinity. You've done problems like this in calculus before. In fact, you started them in Calc 1. By this, I mean the integration going up to infinity is what I'm referring to. You've seen that, but it's not something like you did a whole bunch of them. You were more common to see ones that went from a number to a number, right? So this might be like a bit of a refresher, especially if you didn't have Calc 2, maybe just last semester. So when we have the limit going to infinity here, the integration going to infinity, we're going to replace that with a notation that's going to be the limit. Let's use... I don't want to use n because we used n, or k, actually k was before, so let's use n now. N to infinity. You can use a little different letter besides n if you want. And this will be from 2 to n now. What technique am I going to use in order to integrate 2 over x ln x?
Use substitution.
Use substitution will look very nicely. So, Jubal, what do you think u might be?
Natural log of x.
Yeah, I think that's a good choice. The natural log of x, which means that du would be 1 over x dx. So the 1 over x dx, and I left the dx off, let's put that in there, would be over here, would be replaced by the du. So this will create 2 over u du. Is that okay? All right, so what is the antiderivative of 2 over u?
2 ln u.
Yeah, so my limit will still be here. I haven't dealt with my limit yet. My limit is n goes to infinity. You're right, it is 2 ln u. And my limits of integration are n and 2. So we will evaluate this at the n. So we have still the limit as n goes to infinity. This will be 2 ln n. Maybe we shouldn't have chosen n. Sorry about that. And then minus 2 ln 2. Now, 2 ln 2 is a number. I don't really even care what its value is, but it is a constant, right? Because what I'm finding here is not really what the value is, but whether it actually is a concrete value or whether it's something that's infinite. So this piece is some kind of a constant. So I'm going to write a number sign, okay? So this is a number value. What about the 2 ln n? What happened as n goes to infinity there? Yeah, Annika? It's going to get infinitely larger, right? Natural log goes to infinity slowly, but it goes to infinity. So this piece is infinity. The second piece is some kind of a number. All in all, what this tells you, this is an infinite limit. So what does that mean? It diverges. So this piece, right, the integration diverges. So that tells us that our summation from k equal 2 to infinity of 2 over k ln 2 also diverges. And somewhere along the way, we want to say how we know. Well, it diverges. I'm running out of space, so I apologize. But it's by the integral test. Right? I'm linking myself back to Theorem 9.10 that said this is the conclusion based on the integration techniques. Any questions about that? Okay, so we're going to take a look at a very interesting series that you might not necessarily anticipate the result for. This is kind of a classic example of a series. It's called the Harmonic series.
Ooh, fun series.
Mm-hmm. Harmonic series. And we're going to start by considering a summation. So we're going to consider the summation from k equal 1 to infinity of 1 over k. It seems like a very straightforward, simple series, right? I'd like for you to note that the limit as k goes to infinity of 1 over k is 0, right? So you might be inclined, based on that, to know or to believe or to think, right, that this series will converge because the sequence itself goes to 0. But if you'll remember, we talked about this last time. That's not enough. Sometimes when the sequence's values like this go to 0, it will converge, and sometimes it will not. So this isn't enough of a condition to actually know for sure. So you may, I'm going to write some of that down, think the series will converge. And even if you don't necessarily know for sure if it converges, at the very least, you know that you cannot use this statement to know for sure it diverges, right? If the limit went to 4, we would know it diverged. But the fact that the limit goes to 0 means that we're at least inconclusive on whether it diverges. So at the very least, we are not, if you will, 100% convinced or 100% sure it diverges. So let's actually consider what this sequence looks like. So this is the summation from k equal 1 to infinity of 1 over k. So this is the sequence 1 over 1 plus 1 over 2 plus 1 over 3. And it continues on indefinitely, right? That's what the sequence looks like. So S sub n corresponds to the summation or the sum of the heights at these discrete x values. So we'll say at the whole numbers or at the whole number values. All right, so I'm going to draw a picture for this. So we'll kind of exaggerate our scale just so that we can draw it a little bit easier. This is going to be 1, and I realize that I'm going to collapse my scale a little bit down here just so that we can get it all in the same picture and make kind of some sense of it. So the first one is 1 over 1. This is 1. And then I have 1/2, right? So this is 1/2. And then I'd have like 1/3. And then I'd have 1/4, and it looks like these. They're not connected because this is a discrete function. We're actually adding these things together, right? So for the purposes of the summation, these are discrete values. All right, so these sums, S sub n, is greater than or equal, oh, let me actually draw this in. If I change this into the integral, right, where I connect it with a smooth function like we did on the last problem, and I were to do this, That's not great. Let's try again. That's better. And I were to find the integral, I would create rectangles. You guys familiar with doing that, right? And the rectangles would have the height of the value on the left. And you can see that each of those heights actually overestimates the area under the curve, correct? Okay, so the S sub n is actually greater than or equal to the area under the curve. And the area under the curve is going to equal the area from 1 to n plus 1 of 1 over x dx. This is equal to the S sub n. Let me write it in here. Oh, I shouldn't write it that way. S sub n is greater than this one, this value. Finishing this out. If we take this integration, this will be the natural log of x. If I evaluated it at x plus or n plus 1, this would be the natural log of n plus 1 minus the natural log of 1, which is 0. So we have just the natural log of n plus 1. But the limit as n goes to infinity of the natural log of n plus 1 is what? A lot like the last one we just did. It's infinity, right? So the S sub n, these partial sums that we're looking at, is actually greater than or equal to infinity. Of course, that's not quite how we think about it, right? Infinite is infinite for the purposes of our discussion here. So hence, the summation from k equal 1 to infinity of 1 over k actually diverges. And it diverges even though the sequence approaches 0. So sequences approaching 0 isn't enough. But sometimes when the sequences approach 0, right, like it does converge. So how do we decide which ones do and which ones don't? There's actually a test that will tell us which ones do and which ones don't, and that's called the p-series test. So this is Theorem 911. The p-series, the summation from n equal 1 to infinity of 1 over n to the p, right? So our last example, the harmonic series, the p is equal to 1, right? 1 over n was equal to 1. So this is any arbitrary power of p. This would equal 1 over 1 to the p plus 1 over 2 to the p plus 1 over 3 to the p, and so on indefinitely. This actually converges for all p greater than 1 and diverges when p is less than 1. Less than or equal to, sorry, get my equal to there, less than or equal to 1. So our example before the harmonic series, p was equal to 1. So p was equal to 1, it's going to diverge according to this theorem now that we have. And there is more justification for why that values are used if you take a look in your book for that. But I want to show you how we use it, because this is a really, really easy theorem to use. The integral test required a lot of work, actually. Let's be real, right? You had to do an integration. We ended up using some techniques of integration. We had the limits going on. It was kind of messy, I mean, like in terms of numbers of steps. But the p-series is really easy. So here is the way this works. We're going to confirm the convergence or divergence. And our example, k equals 6 to infinity of 4 over k to the 1/2. Where k starts is irrelevant, all right? It doesn't make any difference in terms of it being convergent or divergent, all right? Usually they will reset it somewhere that's far enough along that it's not going to affect anything. If you had something in the denominator, maybe that would make something equal to 0, stuff like that. But the convergence or divergence does not hinge on that. All we have to do when we're taking a look at this is to recognize that it's in the format that we saw up here. Is it in this format? Ignoring then the n equal 1 at the bottom. Yeah, it is. I've got 1 over n to the p. I actually have 4 over, again, the 4 doesn't matter. It's a constant multiplier. It doesn't change convergence or divergence. It just makes it bigger, whatever it was. So I have it in this format. And what is the p-value here? 1/2. The p-value is 1/2. So will this converge or diverge?
Diverge.
This will diverge. And the reason is because the p is equal to 1/2. So this is divergent. It says diverge, we'll say, by the p-series test. So this converges by the p-series test because p is equal to 1/2, and clearly that we know 1/2 is less than 1, right? The fact that 1/2 is less than 1 means that it's going to diverge. Any questions on that? All right.